Okay, in this video, I want to introduce the idea of statics. So, statics has one very important criteria. Nothing is moving. That's it. And so, if nothing is moving, the physics, what that means, is that the sum, the vector sum of all the forces on the system is equal to 0, and the vector sum of all the torques on the system is equal to 0. Not only is the vector sum of all the torques equal to 0, that also implies that the vector sum of all the torques about every point is 0. And that's it. And so, considering that most departments, engineering departments, offer an entire course just on statics, you can guess that it's probably more involved than simply writing down these two equations, and that's true. Statics problems can get quite complicated, but the fundamental physics is no more than that. So, if you're analyzing a system that is static, not moving, and you want to explore it, what you want to do is first identify your forces. And once you do that, you can apply N2, you vector sum the forces to 0. Okay. Then you'll want to choose an axis of rotation. And like in all cases, you can choose any axis of rotation, but some axes are more judicious than others. For example, if you choose an axis of rotation at a point where many forces are acting, then the torques due to all those forces are 0. Perhaps if you want to choose an axis of rotation at the center of mass of an object, maybe, then the torque due to gravity is 0. There are many different choices, but you have to go ahead and choose an axis. And once you choose an axis, then you can find the torques for each force. Okay. And once you find the torques for each force, you can vector sum the torques to 0. Okay. And so that's to keep in mind, is that the torque of each force is 0 if the vector from the axis of rotation to where the force acts is 0, and also the torque is equal to 0 if the force associated with that torque is parallel to the vector that points from the axis of rotation to the place where the force acts. Okay, and since there really isn't anything more to that, I want to go ahead and just do an example to see how statics work. And I want to do an example that's a little complicated because the physics is just the sum of the forces and the sum of the torques is 0. All right. So, in this problem, I'm going to roll a ball over a step. So a step, I'm going to say roll a cylinder over a step. Okay. So the step has a height h. And so I have this ball, so I need a circle here. Okay. And so this ball has some radius r. So I'm going to draw the radius to this. This is where it's contact with the step. And so this has radius. I'll write this over here. Radius r. And so I'm going to apply a force to the very top of this ball. And at the moment, it's static in that it's not moving. And I want to find the force necessary, this is in contact here, that's going to lift the ball over this ledge. Okay, so since at the moment I'm sort of immediately before, right before I get the force necessary to lift it over, nothing's moving, I can analyze this system using statics, my forces and my torques. Okay, so let's look at the forces first. What are the forces on this object? Well, I have this force here that's trying to push or pull it over the ledge. I have a contact force here, and I have a contact force here. And so I don't have it's not sliding anywhere on anything, so it's certainly not sliding at the bottom, and so there's no force of friction there. I don't have to worry about the force. I just worry contact force. Okay. And so, all right. And so let's draw a free body diagram and get those forces here on the. So I have this force that's trying to push or pull it over the edge. Okay. I have the force due to gravity that's acting down. I have the normal force from the ground. I could say it's a contact force, but we'll just call it the normal force. And then I have the contact force of this corner on the object. And so I mean, it's just a contact force, right? And so often what we'll do is we'll split the contact force into components, friction and normal. I'm not going to do that here. I'm going to break this contact force into components that's just vertical and horizontal. Because so that's going to, I think, simplify, get everything on one coordinate system. And also, I'm not, the parallel to this surface may be tough to do. And so I'm going to look at just the vertical component of the contact force, I'm called V, and I have a horizontal component to the contact force, which I'll call H. So I can do that. I just remember I have some contact force between two surfaces. It was convenient in many ways to break it into a frictional and a normal, but here I'm not so worried about that much as I'm just breaking it into a horizontal and a vertical. Okay, so since everything now is plus X plus Y axis, I can just look at the X and Y axis separately. So at the moment, nothing is moving. So in the X direction, that means the magnitude of the pushing force must equal the magnitude of the horizontal component of the contact force between the corner and the ball. That's these two here. So in the Y direction, then, since all my forces are along the coordinate systems, I have the magnitude of the normal force from the ground on the ball, which is here, plus the magnitude of the vertical component of the contact force between the corner and the ball must equal the magnitude of the force due to gravity on the ball, which is the mass times g. Okay, so I have relationships now between a number of my parameters, but I'm not going to stop there. I'm not just going to look at forces. I want to analyze my torques as well. Okay, if I'm going to analyze torques, then I'm going to need, let's get a yellow here. If I'm going to analyze torques, I'm going to need an axis about which to analyze torques. And what I'm going to do is I'm going to analyze my torques about this point right here, which I'll call O. This is the point with a contact point between the edge and the ball. And the reason I want to do that is if I choose the I think this thing is going to rotate about this point to get up the ledge. But I also think if by looking at it there, then any of the torques due to that contact force, I'll go to 0, and that might save me some math. Okay, so the first thing, the torques for the contact from the corner, well, let's just say the torque due to that horizontal component plus the torque due to the vertical component of those two of that contact force is equal to 0. Okay, so the next is the contact due to the pushing force. And so, well, let's get a vector, fine. So that is equal to the R cross F, okay, where F is the magnitude is the force, and R is the vector that points from the axis of rotation to the place where the force acts. I'm going to, I think, conveniently do this in terms of the magnitude of the force times the component of that radius vector perpendicular to the force. Remember, this is the force times the magnitude of the force times the lever arm way to look at this problem. And so if I do that, if I look at the axis perpendicular to that force, then the lever arm then is that yellow line. That's the component of that vector perpendicular to F. Okay, and so can I calculate what that is? Oh, then I need a coordinate system here. So if I say Z is out of the screen, then R cross F is into the screen, so it's the negative K hat. Okay. Remember, I'm going to clutter up my diagram, but my R vector points from the axis to the place where the force acts, and so if I do a index finger, middle finger along F, I get my thumb pointing into the page. Okay, so I need to look at a little bit my diagram here. And so this total height from the bottom to the top, well, that's 2h. Okay, so here's the center. So 2h, 2r, of course, radius r. And so here's r at this halfway point. This point in here is h. And so this yellow line, the lever arm, then, that the force, the pushing force acts, is going to be twice the radius, this full length, minus the height of the step. So the torque due to the force is F times 2 times the radius minus h. And it's in the negative k hat direction. All right. So now I need the torque due to gravity. So that's r, this r vector to the place where gravity acts, times the force due to gravity. Okay. And well, now, again, gravity acts at the center of mass. So it acts there, and the radius vector that points to that has a magnitude equal to the radius of the cylinder, but then it points off. And so what I want, again, if I'm going to look at the lever arm, I want the component of that radius vector perpendicular to the force due to gravity. And that's equal to this length right here, which I'll call d. Okay? So the torque due to gravity is equal to that distance, d, well, the magnitude of the gravitational force, mg, that distance, d, and if I do a right-hand rule, I get a negative k. Now I'm going to say d because it's not, may not know exactly what d is yet. And finally, the torque due to the normal force, then r normal cross the normal force. Okay. And so that now is equal to again, sort of the normal force times the lever arm, the perpendicular, the component of the r vector perpendicular to the normal force, but now the normal force is just pointing up. It's in the opposite direction. Right here, this is the normal force, in the opposite direction of the force due to gravity. So if the lever arm is the same as the lever arm due to gravity, which is d. And then if I do a right-hand rule, that's positive k. All right. So now let's, if I sort of add all my torques together and say it's static, so my torques are equal to 0, everything is in the k direction, or negative k direction, and so I have normal force times d plus the force due to gravity, mg, times d, and then minus the force, pushing force, times 2r minus h, and this is now all equal to 0. Now, the normal force I find from up here. All right, I have to be careful. I did make a mistake back here. I did my right-hand rule wrong. Back here, this is in the negative k direction if I do my right-hand rule for the torque due to the normal force. And so that gives me a negative here. And so I have that now the normal force is equal to, if I bring this on the other side, divide by d, mg, divide by d, and so I get mg minus f times 2r minus h over d. All right, so I think now is the time to get serious about understanding what this lever arm is for the gravity. And it's a little not too bad, but I just have to do some trigonometry. Note that if this distance right here, which I'll call A, makes a triangle with D, where the hypotenuse here is the radius of the circle, that's r. And so from that triangle, I know that a squared plus d squared is equal to r squared. And a then is simply r. The radius of my circle is r. The a then is r minus h. So I have down here r minus h squared plus d squared is equal to r squared. Or d squared is equal to r over r minus h squared. So d squared is equal to r squared minus r minus h quantity squared. So that's r squared minus r squared plus 2rh minus h squared. So d is equal to the square root of, I factor out an h, and 2r minus h. Okay, a little complicated, but not too bad. Okay, so then I have substitute that into here, and I get the normal force is equal to mg minus f times this quantity, 2r, I'm going to need more room here, 2r minus h over the square root of h times the square root of 2r minus h. Okay, well, this 2r minus h divided by the square root of 2r minus h is just the square root of 2r minus h. So this n then is equal to mg, and this simplifies kind of nicely, f times the square root of 2r minus h over h. So this now I have an expression for the normal force of the ground on the object in terms of my geometric parameters, the pushing force and the force due to gravity. Now the force at which it rolls over the edge is the force at which the normal force goes to 0. And so that we can now solve for, because then that force then is equal to mg times the inverse of that, h over 2r square root of h minus 2r over h. So I maybe better. This force then is equal to this coefficient of geometric terms, h divided by 2r minus h times mg. And this is the force at which the normal force goes to 0 and it comes off the ground. Okay, so this was more of a complicated example. And so it shows that even though the physics of statics may be simple, applying it can be quite complicated. But as long as you take the care to follow this procedure, you can get the relationships necessary to bring everything together. Identify your forces, do Newton's second law. We didn't use these relationships here, but often you will have to. You have to identify your forces, because then that allows you to find the torques. Choose an axis of rotation about which you want to analyze the sum, the torques, and then do the vector sum. And then it's just a matter of big picture, so you can take care to find all the proper angles and to do all the cross products to be able to calculate the right value of the torques, and then to be able to do the right hand rule so that you know which torques induce a positive rotation and which torques do a negative rotation.